Let's check the values of these floor functions for small values of n and see when is n uniquely determined. When n is equal to 1, we have 1/4, the floor is 0, the floor of 1/5 is 0, and the floor of 1/6 is 0. When n is equal to 2, these fractions are all still less than 1, so the floor is going to be 0 again. When n is equal to 3, the floors of these three are going to be 0. We get our first change when n is equal to 4. The floor of 1 is just 1, and the rest of these are 0 again. When n is equal to 5, this floor is still 1, but this floor becomes 1. And 5/6, the floor is 0. As n increases, our floor function will sometimes increase. So we have that n equals 4 is uniquely determined by these functions. When n equals 6, we have the floor of 1.5, which is 1, the floor of 6/5, which is 1, and here we go up to a floor of 1. And at n equals 5, we have uniquely determined floor functions. We see that our numbers are uniquely determined when one of our floor functions transitions from one integer to the next, and then it happens again where another floor function transitions from one integer to the next. So in this example, when we go from 3 to 4, our number becomes a multiple of 4. And then our next number again switches to a multiple of 5, changing this floor function. So whenever we have two consecutive numbers that are multiples of 4 and 5, or 4 and 6, or 5 and 6, then we will have uniquely determined floor functions. These floor functions increase when n is a multiple of one of these three denominators. Multiples of 4 and multiples of 6 are even numbers, so we're never going to transition from one number to the next and go from a multiple of 4 to a multiple of 6. So we have 4 cases. We have a number that is a multiple of 4, and then the next number is a multiple of 5, or we can go from a multiple of 6 to a multiple of 5, or we could go from a multiple of 5 to the next number is a multiple of 4, or we can go from a multiple of 5 to a multiple of 6. We notice that when we count these first two cases, we're going to count numbers that are multiples of 12 twice, once when we count the multiples of 4 and once when we count the multiples of 6. Since these multiples of 12 are counted twice, we're going to subtract them. We have the same problem here with case 3 and 4. We're going to subtract the numbers that are multiples of 12 when the previous number was a multiple of 5. We'll start with case 1, where we have a number that is a multiple of 4, and then the next consecutive number is a multiple of 5. We can set them equal to each other. In mod 5, 4a is equivalent to 4, which means a is equivalent to 1. So a is 1 more than a multiple of 5. We're going to count these for all integers less than or equal to 600, substituting for n, and solving for x. X can be all the integers between 0 and 29, giving us 30 values. In case 2, we have one number that's a multiple of 6, and the next number is a multiple of 5. We'll set these equal to each other. 5b is equivalent to 1 in mod 6, which means b is equivalent to 5. So we can write b as 6x plus 5. Counting the numbers less than or equal to 600, we substitute for n. Solving for x, we get x are the integers between 0 and 19, which gives us 20 solutions. Since we double counted the numbers that are multiples of 12, we're going to subtract the solution to this system. We'll set these equal to each other. In mod 12, 5b is equivalent to 1. So b is equivalent to 5, and it's 5 more than a multiple of 12. Counting the number of solutions less than or equal to 600, we substitute for n. Solving for x, x is an integer between 0 and 9. This gives us 10 values which have been counted twice in the previous two cases, so we'll subtract this. Now we'll do cases 3 and 4, and we'll subtract the cases when n plus 1 is a multiple of 12, because that will have been counted twice. In the first case, we have 5a is 4b minus 1. 4b is equivalent to 1 in mod 5. b is equivalent to 4, 4 more than a multiple of 5. Counting for n less than or equal to 600, we get 30 numbers that satisfy this. In case 4, we'll take this mod 6, which means we can write a as 6x plus 1. Counting again, we have 20 values for this case. Here a is 7 more than a multiple of 12. This inequality gives us 10 values. So we'll add these solutions. We have 30 for case 1, 20 for case 2. We'll subtract the 10 that are double counted, 30 for case 3, another 20 for case 4, and subtracting again. This gives us 80 for our solution. There was one more disputed solution. We'll illustrate that here by looking at values of n around 600. When we get to n equals 600, it's a multiple of 4, 5, and 6. So each of these floor functions increases. If we're restricting ourselves to n is less than or equal to 600, at this point we could say that 600 is uniquely determined, but it is not uniquely determined for all positive integers. The MAA decided that the problem statement was ambiguous, so they accepted that 600 could also be uniquely determined, adding 1 to our previous solution. So these were the 2 acceptable answers to this problem. If you'd like me to solve another AMC or AIME problem, please leave it in the comments.